Right, we want to differentiate this expression. X squared plus 5y to the 4 is 3x cubed minus 2y plus 3. We want to differentiate it. So when we've seen differentiation before, we've always ended up with y or another variable equals something. So x squared plus 3x plus 2. That's what we're used to seeing when we differentiate. Sometimes we have to rearrange, that's fine. But we're used to seeing that. Now I think everyone should pause the video and they should attempt to get this above expression into that form. Can you get that into y equals something in terms of x? And just x, mind. So pause the video and attempt to get it into this form here. Okay, so hopefully you will have had a play with this and found out that you can't actually rearrange this so that you get y equals something without there being a y function on the bottom. So some function in terms of y, which means if we've got that, we're no better off. We still can't differentiate this thing because we've still got these y's to deal with. So, what do we do? Well, we use something called implicit differentiation. And implicit differentiation is using both x and y, differentiating, but compensating for one or the other. So if we differentiate everything with respect to x, when we differentiate with respect to y, we have to compensate so that everything kind of remains differentiated with x. Okay, so I'm going to differentiate with respect to x, and I would write that. Every time I tackle a question, I'm going to say to my examiner which variable I'm going to differentiate in. Okay. Now we know some notation for differentiation. We know that the operation differentiate, we normally use this. So d by dx. And we know that when we differentiate an expression, we just differentiate each term in as it comes along. So if we had an x squared, we differentiate x squared. If we had a 3x, we differentiate 3x. We wouldn't try and differentiate x squared plus 3x. So I'm going to apply this differentiate with respect to x to each aspect of our function here. Actually, right. 5y to the 4. So all I've done is say I am going to differentiate each part of this expression in terms of x. Okay, so the first one I'm happy with, and I hope you are too. Differentiating x squared with respect to x will give us 2x. So I'm going to leave that one as it is for now. What I'm more interested in is this one. Differentiating 5y to the 4 with respect to x. So there's no x variable here, so we can't actually differentiate with respect to x. But we do need to differentiate this term. We can differentiate it with respect to y. If we had differentiating with respect to y, we would get, well, we'd differentiate that with respect to y, wouldn't we? So we'd get 20 y to the power of 3. But that's not in terms of x anymore. We're no longer differentiating with respect to x. So what we've told our examiner is now complete rubbish. If we were to differentiate this, we'd be differentiating with respect to y, and we're no longer differentiating with respect to x. But we know a little function thing that we can put in that kind of cancels out this y, and we've used it before in the chain rule. So in the chain rule, we introduced a variable, and we kind of said, well, if we've got dy by dx, we can say that that's dy by dt multiplied by dt by dx. And in that sense, it kind of cancelled itself out, didn't it? That t and the t cancelled, and we were left with dy by dx, which is why we could say it was equal. So if we introduce dy by dx, then to some extent, this dy here cancels with this one here. So we're suddenly differentiating with respect to x again. So it's a bit of a cheat, but this is why. Okay, so every time we see a y function in part of our expression, we're going to have to introduce this little trick. Differentiating with respect to y, and then adding in this dy by dx. So let's go through each of these sections in turn. So we had differentiating x squared. And then we had differentiating with respect to x, 5y4. Okay, I'm just going to focus on this side of the equation just for a minute, just to give you some examples, and then I'll leave you to set the rest of it for yourself. So differentiating x squared with respect to x is 2x. That's just standard differentiation. This second part, we can't differentiate with respect to x, we can differentiate with respect to y. So we have 5 times 4, so that's 20y to the 3. But because we've differentiated with respect to y, we have to compensate with our dy by dx. Okay, pause the video and finish off the rest of it. So this was 3x squared minus 2y and 3. Don't forget to apply dy by dx to each of these terms. Pause the video, differentiate all of them, watch out for this one of course, and play to find the answer. Okay, so I realise I made an error above, so hopefully you've corrected that. That should be a 3, and that's now just a splod. So let's try that again. That should be a 3. So, differentiating 3x cubed with respect to x gives us 9x squared. Then this differentiates to minus 2 dy by dx, and the reason for that is we're back in the y variable and we want to be in x, so we've had to compensate. And then differentiating 3 with respect to x was just a number, and numbers disappear when you differentiate when they're on their own. Okay, so now we've differentiated this expression, but it doesn't look particularly pleasant to me. Don't know about what you think. I will rearrange this so it says dy by dx equals, because we were asked to differentiate, so we may as well leave it in a form that we recognise, i.e. with a differential function first. So 20y cubed dy by dx plus 2 dy by dx is 9x squared minus 2x. So all I've done is moved the dy by dx expressions onto one side, the x expressions onto the other. Now I'm going to factorise as much as I can. So dy by dx is multiplied by 20y cubed plus 2 is equal to 9x minus 2. So dy by dx, the differentiated version of this expression is 9x minus 2 divided by 20y cubed plus 2. The benefit of keeping it in this kind of form is that now we can find stationary points, we can find gradients, we can find the equations of tangents and normals, because we have dy by dx. And of course that is our gradient function, so it tells us for any values of x and y what the gradient of that curve, that line is going to be.